Numerical Simulations in Engineering and Science. This course is brought to you by Gilad James Mystery School. Learn more at giladjames.com. Introduction. The nuclear reactor systems are sufficiently complex that there could be the possibility of an accident followed by the release of fission product, FBs. Such a release could require multiple failures of safety systems and barriers. In the case of a break in the hot/cold leg in a pressurized water reactor, PWR, coolant and energies are first released from the reactor coolant system to the containment through the break. The FB also released along with the coolant. This type of accident usually occurs in the high-pressure cold leg. The worst condition of such an uncontrolled break is the guillotine type of break. In such type of accident, the envelope of primary systems is breached. If such an accident is not controlled by safety systems, then such accidents may transform into the severe accident. In severe accidents, FB is released during the progression of accidents. Owing to the strong influence of thermal hydraulics on FB release and transportation, FB release and transport mechanism is very complicated and complex. The FB behavior inside the containment is the fundamental of the source term. The source term results are the outputs of level 2 PSA, which are necessary for radiological assessments and consequences. The dominant FBs that constitute and hazardous effects can be categorized as noble gases, Z, Kr, volatile, I, Cs, Te, semi-volatile, Ru, Ag, Ba, senior, Tc, Rh, and non-volatile, Nb, Zr, Y, Pd, La, Mo, Tc, Nd, Se. The aerosols are 129 Te, 127 Te, 105 Rh, 103 Ru, 105 Ru, 137 Cs, 138 Cs, 89 Sr, 90 Sr and 140 Ba. These isotopes release in the particulate form, and going through agglomeration and nucleation process, they form aerosols. However, iodine may transform into volatile species and possess a complex chemistry. The common organic form of iodine is available in chemical forms as Che, Chi and Hai. The behavior of FB is highly influenced by the in-containment atmosphere, heat loads, containment pressure and steam generation rate. The containment is installed with a spray system and cooling fans to prevent the early overpressurization due to the heat load. The containment spray system is significant in enhancing the early depletion of radionuclides during early in-vessel release phase from the containment atmosphere. The spray system is automatically activated, as an emergency design device to prevent containment integrity. The FB released from a nuclear power plant, NPP, is known as a key factor affecting both the design of safety equipment and safety evaluation, including safety and risk assessment. Experimental research on FB release behavior was conducted by many investigators. Many experiments had played a significant role in understanding the behavior of aerosols, FBs, iodine chemistry, and transportation under accident situations. The Phoebus FB project was the most impressive program initiated to study the behavior of FB. The main objectives of this project were, 1. To minimize the uncertainty in source term evaluation, 2. To study the FBs, structural and control rod material release transportation and deposition from the degraded core through coolant, and, 3. And behavior of FB inside the containment building. Meanwhile, several analytical and computational codes were developed. ASTEC is one of the most popular codes used to study the behavior of FBs in severe accident conditions. Melker along with Mix can be used to assess FB release and assessment of radiological consequence. MOP is the most popular tool to calculate severe accident source term, and its quick calculation is its prime character. Therefore, MOP code is widely used in the nuclear industry. Moreover, the numerical simulation of FB activity has been carried out by several researchers. Have developed an analytical model FIPRAP FB release analysis program for the numerical simulation of FBs released from the fuel. The FIPRAP code can estimate the volatile FBs released from the nuclear fuel under changing irradiation conditions with the incorporation of all physical phenomena and fulfill the requirements of fuel designing, performance, degradation and source term estimation codes. Lewis et al. Have presented a review of FB's release modeling in support of fuel failure monitoring analysis for the characterization and allocation of defected fuel. A generalized model for FB transport in the fuel-to-sheath gap was given by Kua et al. Have proposed a model describing pallet oxidation and bubble formation at grain boundaries, their interlinkages, and release into exposed surfaces. Avanov described a good model for the description release of FBs from the porous ceramic fuel, its leakage from cladding and mixing with the primary coolant. Tucker and White have proposed an analytical model for the estimation of FBs from ceramic UO2 fuel. In this model, the PF leakage probabilities from the fuel interior through grain are figured out. These probabilities strongly depend on the interconnectivity of pores in the ceramic fuel. Awan et al. Have also carried out the numerical simulation of FB activity in the reactor primary coolant. The proposed developed model is hybrid and analyzes the static and dynamic FB activity in the primary coolant of the reactor. The goal of this lecture is to carry out the numerical simulation of FB behavior inside the reactor containment building under LOCA using MATLAB. The calculation process of iodine and other FBs is shown in. A semi-kinetic model has been developed and implemented in MATLAB to carry out the sensitivity analysis of FBs during postulated LOCA for typical 1000 MW power. The kinetic model is presented in section 2, which contains the deterministic as well as the kinetic approach. The deterministic computational methodology and computational steps flowchart are described in section 3. Next, the flowchart of model and implementation of model in MATLAB are described in section 4. The examples and outcomes of the simulation results are presented in section V. Finally, section VI is the conclusion. The calculation process of the FB behavior inside the reactor building.